Cool. So yeah, thank you for the introduction. Chaos engineering, this is something I work at Datadog. I'm a site reliability engineer. I'll talk about what that means if you're unsure about that title. Or actually, I'll talk about it now. So before there was the SRE, there were two kind of roles. There was DevOps and software engineers. I'm pretty sure most of you know what a software engineer is. But DevOps was the person who took care of the infrastructure on a larger scale. So the software engineer made the services, and then the DevOps person made sure that the services were running correctly. And so SRE is just essentially a merge of these two. So someone who makes automation for the infrastructure. And it's in the name, but reliability is a big thing, and that's it connects with chaos engineering. So what is this like super edgy engineering field? So it's automated infrastructure level failures. So I'll use that word a lot, which is infrastructure level failures. I'll just keep it to failures as I go on. But essentially, this is stuff that happens to the infrastructure that is we don't want to happen. So servers going down, network having some kind of latency or something weird happening to the network in our infrastructure. So the automated part is doing this on purpose, which seems kind of weird. Why would you on purpose break these infrastructure level things? But there's actually a really good reason for it. And then of course you want to make sure that you're cleaning up this kind of mess that you're making in the infrastructure. And again, we'll talk about that as well. And then randomness is key, because if it's not random, it's not chaos. Okay, cool. So I don't know where I found this quote. I just remember it. So chaos engineering is like giving your infrastructure a flu shot to better prepare for the real thing. It's basically that. So infrastructure level failures or failures, they happen rarely in certain companies, but when they do happen, we have like outages, which affect customers, and customers get really mad. So in this sense, you're giving your infrastructure like a little dose of what it would actually look like if your infrastructure failed. And it gets better because people who are making the services, software engineers, they see this as a common thing rather than something that is rare. And if you know it's coming, you can better prepare for it. Because I don't know who quoted it, I'll say that I quoted it, and you guys can like put that somewhere. So before the chaos, so this is what was done, or what was the idea before chaos engineering was even a thing. Just for reference, some companies that are doing chaos engineering, one Datadog, and another big one is Netflix. So the software engineer's job is to make services, so make some kind of application, and then test it really well. So you can't test like 100%, but people try. But testing your services or your applications, it's pretty easy. What people do right now is as soon as they make a change or they update a feature, it goes through like lots of phases of testing. And so this makes sure that once the feature is in the product, there are not that many issues that happen, no bugs, things like that. Of course, some things slip through the cracks, but this testing is pretty rigorous. But there is no testing for infrastructure level failure. So these failures, it's very hard to test, right? Every time you push a feature, you don't want to be hamming your infrastructure, because there's a lot of features that go out in a day, usually. But yeah, so if we don't have these like failures or these tests, it becomes difficult when those rare scenarios happen to deal with it, because we didn't know it was possible, or yeah, that's basically it. We didn't know it was possible in that sense. So there's like several different kinds of infrastructure level failures that we'll talk about later on, but some of them being network latency skyrocketing. So if your customer is dealing with your web application and say like most of your servers are down, then there's going to be really high network latency. So instead of the customer getting their page and data in like less than a second, they'll get it in like a minute or something, and this will cause your revenue to go down because people will stop using the product. And so software engineers are just kind of like, shit, what do I do? Because these are pretty rare and I don't know how to test it. And that was before the chaos. But yeah, so this goes into the start of controlled chaos. So if you can't put it part of your rigorous testing every time you push a feature, you want to put it a part of something you do manually. So you'll manually go with your team or whoever is responsible for this service or feature, and you'll try to break things on purpose to see what the outcome is. So I'm going to guess that not a lot of people are familiar with distributed systems. So in a sense, if we have, say you're a company and you have a website, and it's like serving content to your customers, most companies have they basically copy a bunch of these servers so that you can give customers faster speeds. Think about it like this: if you have a supermarket and there's one cashier, it's going to be really slow to get a checkout. You have multiple cashiers, it'll go a lot faster. And so we have several servers, and they all have a copy of the service. And so we're going to do some manual chaos testing. So we call these game days, and they're essentially what I said, which is like everybody sits in a room, and they do things like take down a server on purpose or do things to the network, and they see how their features or their applications face after this, right? So let's say you bring down a server and your assumption is, okay, if I bring down the server, it'll be fine because there's other servers that are alive. And so there shouldn't be that much of an issue. Maybe the network latency will go up a bit, right? But what happens if you take down a server and your entire application stops running? So this is a problem and something that could happen. And you want to catch these cases. But this is like lots of manual work, right? So like I said, a bunch of features going through a company and being merged into their repos. And so if you wanted to do this correctly, you would have to game day every single one of those features. And that's way too much. And these game days, they usually last like around 1 to 3 hours, in my case at least. So for each feature, which there could be like thousands every day, 2 to 3 hours is just not realistic. And also keeping track is difficult. So we haven't got to automated chaos testing yet, but keeping track of things that are important for every single test that you do, it can be difficult. At Datadog, we have a specific framework that we use, which I'll show you. But it can't be something as shallow as, okay, I wanted this to happen and this is what happened, right? You need more context for people who are going to do it in the future. And for you, if you forget what happened to the current game day. And so this is the framework that we use at Datadog. So you define the failure, what was the goal of it. So let's say you guys put in a new feature for your web server that if one pod goes down, all the other servers will be like, hey, server. If this server goes down, then all the other servers are like, hey, the server is down, don't send anything to it anymore. This is a possible solution to if a server goes down, right? So that would be the goal, that would be defining the failure as in we're gonna take down a server, and that's what should happen. The command, so there's a bunch of different commands that you can use to simulate failure. I'll talk about some of them later. What is the expected outcome versus the actual outcome? So I think this is pretty self-explanatory. The expected outcome is it works, and then the actual outcome is usually that it doesn't work. But of course you want to put more detail. So the actual outcome being like what exactly happened. And if the actual outcome is not expected, what are some potential reasons for this? So you can't just say this is what happened and then start digging into the logs or whatever information that you think it will be necessary here. You need to first come back and think about why this could have happened, because it'll make it a lot easier when you're digging into your logs. And then action items. So it's important that if something did fail, you want to do something about it. Cool, so this is something I previously talked about. So if there's a bunch of different features going out every single day, it's not realistic to be able to game day each and every one of them. Sad face. And so now we get to the last part, which is the automated chaos. And so I think another half of this is going to be just talking about like the different kinds of failures, which are really cool. But yes, automated chaos. So this is where the SRE portion of my job kind of lines up with this. So chaos engineering is a way to ensure reliable systems, because if software engineers are creating these services and we are automatically doing these game days, they're more aware of them, and they don't become this rare occurrence anymore. They become more of like a thing that happens every so often, and so they can properly add code to their services that makes sense to kind of fight these different game day scenarios. So the automated game day, or the chaos toolkit as we call it, does common failures. So common failures are things like taking down a node, adding latency to a network, DNS issues, which we'll talk about, and things like that. So we can automate these, and we can basically make that framework that I talked about before. So we can do that just by looking at the logs and everything that's happening in the infrastructure. So we can define what the goal was supposed to be. If we take down this server, this should happen. And we can automatically just create this framework for future game days. And so one thing is timing is like really important in terms of randomness. So if you are running this automated failure every like 10 a.m. of the day, and teams are aware of this, then they can easily just like do something to their service that kind of skips the game day, right? So that wouldn't be much chaos engineering because they're aware of it. So we make it random every single day. This way they have no idea when it's going to happen, but they know it's going to happen, so they have to be prepared for it. And so this is cool because the randomness makes people really grumpy, and that's fun. Okay, so now we're going to go into like some examples, but to understand the examples, you need to understand Kubernetes. So I'm going to do like a 101 of this. Just these things are all you need to understand the next following slide. So I'm going to do some drawing. Okay, so the service. Can everybody see? Cool. Okay. The service, I'm pretty sure most of you know, it's like the application, right? Okay, that's the application running. Some web server, some database, something that's running. It's running code. Then the pods. So in Kubernetes, pods are just a group of services. So here's a pod. So there's a bunch of services in here. And they may be talking to each other. Cool. And then deployments. Deployments are a group of pods. So this is a deployment pod. So let's just say these are pods. These are pods. Nodes. Does anyone want to guess what a node is? A group of deployments. Holy shit, it's like these Kubernetes guys are crazy. They're so smart, holy shit. Okay. So yes, they're a group of deployments. A node is a server in another sense. That's how Kubernetes sets it. So a server can have a set of deployments running in it, but the deployments can also be in different servers. So here are some deployments. So again, there's pods in these guys as well. Cool, what's next? Node groups. Does anyone want to guess what a node group is?
A group of nodes.
Wrong.
Oh.
Just kidding. Yes, it's a group of nodes. So I don't think I can make a bigger box. These guys are connected. And then namespaces. So a namespace, it doesn't follow the trend that we've been currently looking at. It's essentially just a way to divide your infrastructure, or divide these things. So let's say you have two teams in some company. One team does web server, one team does the database, and you want to separate the deployments and all the pods and everything. So namespace is a way of dividing them, saying, okay, all the deployments that have the namespace like database, DB, those are specifically database services. And everything that has like WebWS in the namespace would be specifically web service stuff. So this deployment belongs to DB. This one could be DB. This one could be WS. And so if you wanted, you could talk to Kubernetes and say, hey, give me all of the give me all of the database resources. So it would give you this one, it would give you this one, and so forth. So namespaces are a way to just divide how the resources are. I'm going to say this is namespace. And then DNS. So forget DNS. What is the acronym? Domain name service. The way that I see it is every node needs to be able to, it needs a name, right? And not only do nodes need a name, pods also need a name. This way, if one pod wants to talk to another pod, or if a node wants to talk to another node, they know each other's names so they can communicate. And so there's usually one server that knows everyone's name. So let's say this is a node, and it has one deployment element, and it has one pod, and then the service that's in it knows all of the names of all the resources. So if this DB deployment, or if the pods in this DB deployment want to talk to the pods on this DP deployment, it can talk to this guy. This guy will be like, yeah, I know who you want to talk to, and it can go straight there because now it knows the name. Cool. So that's DNS. Before we continue, I think that's the last thing on that list. Is there any questions? Anything that's unclear? Yes?
So all these services and pods and whatever, they're all logically grouped, right?
Mm-hmm.
It's not physical at all.
All logical. Okay, cool. Yeah, if there are any questions, feel free to raise your hand. I know this is like a lot, but it's also necessary to understand the next few parts. Kubernetes is a bunch of different other things, but these are like the most important things that are necessary for the next step. Yes?
You might give some examples on what would be contained those things. Like, so you say services, and then you say pods, but can you give like a more general example of that?
So
What would be contained in those?
yeah. So let me just frame it into something that we're all familiar with. So the node, like a computer, like a server, right? In the node, there are what's called, like, there's Kubernetes applications that do this logical definition of everything. So if I talk to this node, it knows that there is this deployment. This deployment will have a name, say deployment 1. And that's logical. There's no like code or anything. There's no servers. It's just a logical thing saying this is deployment 1. And inside deployment 1 is pod 1. And then inside pod 1 is server service 1. So all of these have a logical name. You can't communicate with it using the network. When I say like you can communicate if you have the name, you need like a specific name for this. These are just logical names. And then there's a specific DNS name used to talk and communicate. So yeah, the pod is also logical. The service, if you really want to get into it, this service represents a container. A container is like a virtual machine, but not really. So as you can imagine, in this node, there are several. The only thing that's actual physical are the services. The services are physical because these are actually running on the machine, and it's something that's real. Everything else is just logical. The pod is logical. It's not real in a sense. Kubernetes keeps like a database of its own resources and says this is the abstraction of a pod, and the abstraction of the pod holds all of these virtual machines running services. That was over-explained and probably didn't answer your question. Sorry.
Like a service would be an example of like a web app that you build. So like
Okay.
yeah.
Okay. Thanks. Yeah.
Any other questions? Cool. And so now we have a list of failures. So these are like the different kinds of automated failures that we can do. We're gonna go through all of them because they're fun. Pod failure. What do you think that does?
You take down a pod.
Whoa. Dude, this is a university. You guys are so smart. Okay, so Yeah. Basically, what we can do in the automation is talk to Kubernetes and tell it, hey, just like delete this pod. Just like act it doesn't exist anymore. So we can completely remove it from existence. And then, so remember this is the deployment for the DB. Remember this DB deployment here communicates with it. So what happens when this DB deployment is trying to talk to this set of pods here? It doesn't exist, right? So this is something that can happen, and it does happen, and you need to think of different ways to kind of like subvert this issue. What may happen is you could talk to these set of pods. They don't exist, so if you try talking to them, you'll get like an error. And then your whole deployment could crash by this. Or you can put something in your code that says, hey, if this guy doesn't respond for like 3 minutes or something like that, then you can assume it's dead and maybe scale up. So because you have one less deployment for database, you may want to scale up and bring another one back into existence. Right? So that's like a potential way to deal with it. A deployment failure. So this is essentially the same thing, but at the larger scale. So now if you take down a deployment, you're taking down like several pods, right? So this gets even more difficult to deal with, but it's also something that's possible. So this entire thing would go down in a deployment failure. And it's scary how easy it is to do this. It's like one command, and all of this is just gone from your infrastructure. And then in that sense, the solutions are basically the same as the other. If you want to try to communicate to anyone that used to be here, you would have to first check against if it's alive, wait 3 minutes for it to respond. If there is no response, then maybe try to scale up, try to create a new deployment. But again, this is a problem and it can happen. The node failure, it just gets bigger and bigger in terms of like the scope of the failures. So if a node dies, then so many deployments die. So now this is at this scale. Now if a node dies, now we have all of these services that are trying to communicate with different namespaces. So we have now the web servers affected, right? Before it was just the database service because it was just the database deployment that was affected. But now the web server is affected by this failure. So bigger failures, but also possible failures. So you need to figure out a way to deal with this. In a lot of cases, it's just waiting and checking to see if it'll come alive. And if it doesn't, to try and scale up. Now this is gonna, yeah.
If you had like a redundant node, if you take down like both and you wanted to like take down one, would you take down all the redundant nodes as well, or would you keep them going and see would they pick them up? Would they pick them up into?
So question, why would you remove all the other redundant nodes?
I mean, just like would you guys like test that to see what happened, or is that you just take down one just to see if it would pick up the other one and replace it?
How many redundant nodes? I just want to go through your thought process.
Oh, because we're distributed. He's been drilling that you would have redundant nodes for every.
Yeah. That's really important. I mean, that's what like most companies do, right?
Yeah. So when you guys do this, do you guys just take down one, or do you take down the redundant ones as well?
So it's a good point to say how many redundant nodes are you going to take down and what's the effect. You don't want to take them all down because at that point there's nothing serving your customers anymore. Because you need one server to do something, right? You need at least one, or some. I mean, at Datadog we need at least 3, right?
Okay.
Yeah.
Wait, so you do chaos engineering in production?
Yeah.
I thought you guys had a backup that you were doing this on. I didn't know you guys were doing.
No. This is in production because this shit happens in production, so you need to be able to deal with it.
So there's like a time where like people are doing stuff on something, and you're like, fuck it, we'll take this down and see what happens.
Yeah. So for this production versus staging, so production is where the real data is being processed for real customers, and staging is where we test things out. You'll find this a lot if you go to different tech companies. They have this idea of like production and staging. So staging is usually always broken, and then production is usually working. And staging is just like a fork of production or a copy of production at some point in time. But yes, we do this in production. So that means when we bring down a server, it is possible that if software engineers didn't make their services resilient to these kinds of failures, we could lose a lot of money. It's possible, but I mean, it works in the sense of keeping software engineers cognizant of these issues, because they will always put more code and more thought into a service that's going into a system that definitely fails, right? And again, like big companies are doing this, like Netflix. Netflix does this in production, and they do it at a crazy scale. Their failures are intense. But yes, so node group failure, that's just at a bigger scale. I don't think I need to go into that. DDoS attack. So this is something new that I actually worked on. So we actually DDoS ourselves. So if you're not familiar with what a DDoS is, denial of service. It's true denial of service. Okay. It's essentially, the way I see it is some entity is just throwing a bunch of requests at your server that mean nothing. And the only reason they're throwing all of these requests at your infrastructure is to try and take it down. So if you're not familiar, when a server is trying to read data from, say, another server, it has like a queue. And the queue will start filling up the more requests it gets. And once the queue is like completely full, in most cases, it just drops packets. So when new packets try to come in, so just imagine if someone was sending false information, whole queue is filled up with all this false information that means nothing. And then an actual customer tries to give you information, it's just dropped. So the actual customer sees nothing. It'll get like a 50, I don't remember the status codes, but some error. And the person who's just sending you fake requests is basically taking down your system by just hitting it with requests.
Are you talking about a SYN attack?
I'm not familiar.
Like some packets over and over again?
That's one way. So it's any kind of request, right?
Right, okay.
So if a person knows that at the infrastructure level, let's say you want to send like an API key. Are you guys familiar with API keys? So this is essentially a key that lets you do things like get data, put data into the server. So if a person knows that the server will always check if there's an API key in the packet, and it won't do any dropping of the packet, because like it's super easy to see a packet, and if there's nothing in it, just drop it, right? There's no reason to deal with it. But if you put like an API key in there and you put just garbage, and you know the server will always check it, that is computation that it's doing. And computation it doesn't need to do, right? So now it's doing all of this computation for absolutely no reason because all the API keys are just false. And this will break down the server. So that's just one type of denial of service. SYN attack is another kind. But yeah, there's actually a tool, an open source tool to do this. So if you want to go to jail and DDoS Rutgers, the link will be there. But we use this tool to DDoS ourselves because we have some load balancers that we want to just attack and see how they'll be affected by this kind of attack. And we do things like we check the length of the API key. So all of our API keys are like 32 characters. So if we get an API key that's like 30 characters or 2 characters, super easy. Just drop those packets. They mean nothing to us, right? And so we add a lot of these strategies. We do rate limiting. So rate limiting is like if we get a bunch of packets from one server and it's maybe like 2,000 requests per second, we'll rate limit them, which means they go into like another slowed down queue. So all the customers are going in the fast lane and everybody else goes in this thing we call a tar pit. So if they're sending way too many requests over, it'll just slow down their process. And that gives us a lot of time to deal with the issue if it is a bigger issue like that. Yeah, so DDoS is cool. Network latency. So there are commands that we have which will increase the latency between communication between all of these resources. So if this database pod wants to talk to the database pod over here, we can use a command that messes with the network. And essentially, what the command does is it tells the network card like, hey, wait 300 milliseconds before you send the packet, or wait some arbitrary amount of time before you send the packet, and it simulates like a slow network, right? And so what do you do in this kind of slow network environment? So remember, for one of the other failures, I said, oh, if it doesn't respond in like 3 minutes, just assume it's dead. What happens if the network is just the slow one? And so what happens if the network is super slow and you're trying to see if this other set of pods is alive, and it is alive, but it's taking way too long to send that packet, then you assume that these guys were dead, but they are alive, and that's not a situation you want to be in. So that's, in a sense, like how you can try to fix one issue, but it actually, fails in other scenarios. Network reject, yeah.
How exactly do you test the network latency?
How do you test it?
Yeah.
Like a solution?
No, like how do you like induce that problem?
Yeah. So there's a command line that you can use. It's actually called Vegeta after Dragon Ball Z. It's the open source one. So it will actually just hold on to the packet, just wait, and then send it. And that's all it does. And it simulates network latency. Like that's basically what it is, right? The other server sees a super delayed packet, and it has no idea. Network reject. So essentially, network reject is, I think it's pretty self-explanatory. Every time a packet comes in, you mess with the network card and you tell it to just drop every incoming connection. So this is another interesting case because if, let's say, these two are trying to communicate with each other, this pod and service. So let's say this guy's sending data and this network card is rejecting it. He thinks this one is dead. And then this one has no idea why this one isn't sending data. So it thinks this one's dead. So now they both think they're both dead. Wait, does that make sense? Like, you're dead. No, you're dead, right? Yes. And that's like a problem that can happen, right? So these are like a bunch of different interesting problems that you need solutions for. You need like the best next thing. So what would be like a possible solution to this if they both think each other are dead? They want to like guess like what you can do in this case.
Duplicate DNS servers?
So right, so this was the DNS. Oopsie. Talking to like another one of here. I don't know if that changes your response.
You go outwards, so you ping like the node.
Yeah. You ping another one, right? So if this guy's dead, or you think it's dead, you can talk to another one. Say this isn't dead anymore. You can talk to this guy and be like, hey, do you think he's dead? This is actually called gossiping. It's really cute, but it has issues. I'm going to talk about it because it's actually really funny. So we had an issue where we had a bunch of different servers, and they were congesting the network because they were gossiping too much. So it was basically just like a bunch of teen girls gossiping with each other, and we couldn't get them to shut up. And so, yeah, it was congesting the network, and it was a super slow network. And when we looked at the logs, all you saw was this node is talking to this node is talking to this node. You saw the entire log of all the gossiping. It was cute, but it hurt us. But yeah, just finding like a different node, part of the same deployment, and saying like, hey, do you think this guy's dead? And so if this guy sees this one is alive and this one is alive, you kind of just fix the issue, right? These two are just like angry with each other or something. They don't want to talk. Network probabilistic ACK. I don't know if that's a real thing. I just came up with it. But basically, it's like instead of rejecting the packet, you throw a dice and you say, okay, 20% of the chance you accept the packet, 80% of the chance you reject the packet. This is interesting. Problem. But yeah, it's essentially the same thing as the problem that we talked about before, which is reject. But it's a bit interesting because now this guy's actually responding to you, but you don't know if in the span of time that it rejects, is it dead or is it a latency problem? There's a bunch of different issues that could be the problem. And it's a little harder to deal with that issue. So we haven't implemented this yet. It's something easy we can implement, but we haven't thought about like solutions for it yet. DNS failure. So remember this guy here, he knows all the names of everybody. So if you want to do any communication, you talk to them first, and then you try to find them and talk to them. So what if this guy dies? So what if they don't know the name of the people? Just randomly dies. So now this guy wants to talk to these guys over here, but there's no communication to DNS anymore. What are some solutions there?
Can't they go to the other machines and ask, hey, do you know this guy?
So
Find it out until they find someone who does.
this is possible, but what do you need? What does like the other people? What do the other people need for them to know about everybody else? They need to have the name, right? Right? But let's say they don't have the name. Let's say they always talk to this guy. I mean, there's a solution here in terms of having the name, but what is the solution?
Broadcast?
Ask everybody.
Well, I heard it.
Cache?
Yeah, cache. So every time you talk to this guy, instead of just like forgetting the name, store it, right? So now you know the name, and unless this guy's name changes, which doesn't happen very often, you're good to go. Even if the DNS is dead, you have a cache of all the names that you usually talk to, and you can just use that to go and communicate with everybody else.
What happens if the name changes?
Yeah. So if the name changes, this is a difficult situation. It's just difficult. But that rarely happens, I think. It rarely happens where the DNS changes. Yeah?
Is it possible for the pod to die or Kubernetes to lose track of the pod, but the services inside it are still running?
Yeah. In that case, you would just have to take down the node. If the logical representation in Kubernetes is not evident to Kubernetes, it's lost. It's just lost. You need to take down the node and then start up a new one. This has happened before. Sorry, sensitive information. What? I don't even know what you guys are talking about. Let's go to the next one. gzip bomb. Oh yeah, what's up?
I have a question for the last one.
Yeah.
Do you actually only just use one node to hold on to DNS?
No.
Isn't that
No. There's multiple.
single point?
But something that we do is DNS usually communicates only through one port on every server. So we block the port. So you block the port, you never get DNS responses. And that's another case where you can just like look at the cache. gzip bomb. This is like my favorite. So does anyone know what a gzip bomb is? Only you? Okay. So basically, you can send. I'm sure you guys like like compressed files before, right? For your classes. So essentially, what the gzip bomb is it starts out as a huge file, and then you compress it all the way down. And so now this huge file looks like this cute little dog, but actually it's like a werewolf. It's like so big, right? And so what happens is you send this request over to a server, and the server's like, oh my god, this is so cute. Let me open it up. Oh fuck, it's getting bigger. And it just like completely crashes the server because it didn't expect it to be that big. So funny story about this, I was creating this attack, and I decompressed it by accident, and my laptop stopped working. Yeah.
What was the fix?
I had to just shut it off. Yeah, it was pretty embarrassing. I posted it on Twitter. But yeah, gzip bombs, they're pretty cool. So, and then the last year is just dealing with the storage. So the storage of a server, it usually is not filled. If it gets to a point where it's about to be filled, maybe like 90%, you may want to give it more storage, and this is possible in cloud providers. So AWS, I'm sure you've heard of it, Google Cloud, they can actually increase your storage as you need it, but sometimes we put hard limits on them because the expanding storage actually costs a lot of money. So we'll set a limit of how many gigabytes, terabytes you want on it. But what you can do is you can like wipe some of the storage, and if you only have one place, like if your storage is unique, it should never be unique, right? You should have redundant data always in like these big servers. And so when you completely wipe the storage of a server, like a database, and so that database thinks it has it, but when it tries to look for that data, it's gone. What's your solution, right? Does anyone want to think about like a solution? Yeah, right? So you just like talk to the other databases and see if they have that data, and then you can easily recreate it. But is anyone taking distributed? Have you guys talked about the, wait, not distributed. I forget where I learned this, but like the parity bits and this. Say again?
Internet technology.
RAID? Is that where you learn it? In internet technology?
Raid's OS.
Oh, okay. Yeah. OS then. So essentially, you can have storages that can rebuild themselves. You need more data, But this is another solution. So just make sure that you have some RAID level that can rebuild itself, and that should also solve the issue. Another interesting issue is like if you overfill the storage. So this was actually something that happened to us. Like we had some servers that had reached their maximum of like 99%, and they couldn't update because to update they need to write logs, and to write logs you need to use storage, and if there's no storage you cannot update. Does that make sense? So these servers could not update, and because they're not updating, there's super old versions of like services that we use, and that's usually like really bad because maybe the previous version is really badly optimized. And there's a slew of different kinds of issues that can happen here. But yeah, overfilling the storage is also another cool thing. There's a command which is interesting for this one that can create a file that looks like it's big, but it's not actually big. If you don't know this, every file kind of has like metadata that says all the interesting information about it, how big it is, what's its name, blah, 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 and then it has all the data. But what you can do is add in the metadata. You can say this file is huge, but there's actually nothing in it. And all that does is it goes to the storage and it like holds like this amount of data and says, no one used this data, even though there's garbage here, there's nothing here, just no one use it. And you can overfill the storage that way, which is pretty cool. Before what we were using was we would manually put ones into storage. So that was way too long because we have servers that have big storages. So that was bad. So the metadata solution was pretty cool. I did say I would talk about some of the commands I use. So for the node failure, what we do is we put an implicit kernel panic on the server. So what this means is the operating system has a way of protecting itself by just shutting down. So think about it like this. If a service, say a malicious service is on your server and it's like corrupting data, if the operating system notices this, its best approach is to just turn off because it doesn't want this service to continue to have this malicious intent. So it just turns itself off. And so we can implicitly put this kernel panic on the server and it'll just kill itself. Yeah, that's pretty cool. Talked about the DDoS tool. What's up?
How does it detect if data is being corrupted? Like, does it what do you guys do for that?
So when it tries to read data and it just has like what's supposed to be there isn't there, like you guys familiar with like OS land, right? OS land versus user. So in that sense, if it expects something in OS lands that's not there, it gets scared and it just dies. Yeah, they're weak servers.
Can't you pack all like the top, like the pod failure, deployment failure, no group parents, like this cozy method? If you figured out a way, like just pack it as a cozy method and implement it in all your features, because it seems like approximately the same solution for all of them. Or do you have to like be very specific based on what your feature is?
Each one has its like own blast radius. So the blast radius for pod failure is very small. If a pod dies, not a lot happens. And as you go further, more and more, the blast radius increases, right? So remember when we took down the entire node, not only was DB affected, but also web server. And so you can imagine in one node, there's like hundreds of different namespaces that divide things up. And so doing this all in one would be devastating. Right? So that's why when you push a feature, you don't automatically just want to run this toolkit. You push your feature, it runs without issues, and then when the randomness decides to do the chaos tooling and do some of these things, you never want to do all of this at once, right? You do them sporadically. And that's just the sense we want to start at a lower scale for a newer service. But if it's like an older service, it should be able to deal with like a node group failure. So we start right there.
So you build it up slowly.
Yes. Yeah.
Do you have any ways of dealing with Byzantine failure?
I forget this. Can you remind me?
It doesn't tell you what one.
Yeah, Byzantine is literally like the data gets kind of funky, and then you're literally just like, well, is it a network issue? Is it like a machine issue? Is it a service issue?
Yeah, so don't know if it'll answer the question, but I have something that I'd like to say. So in terms of like like these weird things that happen, without this chaos tooling, this is usually what people see, right? So we don't know if a pod went down, we don't know if a node went down. All we see is like Byzantine errors. Like it just gives us like error in the logs, right? Sometimes. And so by doing this and having a record of like, we applied a pod failure, we applied a node group failure, Byzantine errors don't become Byzantine errors anymore, right? They're kind of defined, right? So this is the best way to define those kind of errors. But yes, I think I'm going to questions now.
You ever get yelled at for errors that didn't come from your random chaos engineering?
Of course. Yeah. Then I just got to send them like the logs and be like, there was no chaos tooling done at this time that you're complaining about. But you know what's cool? My tools can fail, but you would have no idea. I could just get away with it. Just be like, no, it's supposed to do that. Those are the links. Yeah.
So after the nodes were gossiping too much, did you guys just disable all the gossiping, or what happened after that?
What was happening? What was happening? So if I remember correctly, the gossiping was happening because basically we added a new update where it was ooming, which is out of memory. And what would happen is the node would start up, it would oom and die. So all of the things are gossiping and like, oh, is he dead? Is he dead? Is he dead? Is he dead? Yes, he is dead. And then they all get that information. But we had like a solution for this. If this goes down, put another one up. And when that other one went up, it oomed again. And so as you can imagine, we just kept spinning up nodes and they kept dying. So the gossip became, is this one dead? No. Is this one dead? Yes. Every new node that came up, there was like a new, like it was exponential the amount of gossiping that was happening.
What was the biggest fuck up you've had at work?
What the fuck is this? What does that have to do with chaos engineering? Fuck. Let's see, the biggest fuck up. Pushing a prod?
Fucking mood.
But isn't that your job? Like literally, don't you push the prod? No.
No, the chaos toolkit is in prod, but we have a staging version. So we push the staging, see if it works, and then we merge it to prod.
Oh, you just push it straight to prod?
No, that's a problem. That's my biggest fuck up.
Yeah, that's what I was saying.
No code reviews. No, just push it right into production.
No, this is horrible. Don't do this.
Regarding like that diagram over there, you said if like two web services think each other is dead, it's like they kind of ask like another web service in this instance. How many other web services do they ask?
Do they ask?
Yeah. How many do they ask? One.
So so this goes into distributed algorithms, like there's like consensus algorithm. So you would want to check with the majority. So if you know that there's 5 servers, web servers, you talk to 3 of them, right? And if you get a consensus from 3 of them, you don't even need the other 2 to talk back. But if there is no consensus, that's another issue.
Wait, but you said like when you did like the network rejection, you would just change the network card so it would reject all packets. So how would pinging another server work? Because that server could just ping and that packet would also be lost. Like, isn't that the case?
So if I'm a server and I reject everything, and I ping another server, I can ping another server, right? Just because I'm rejecting packets doesn't mean I can't talk. Like it's not a one-way kind of thing.
Like, if you can't tell if a node is dead, so you try to do the gossip, but the node that seems to be dead is rejecting all packets. How is that?
Yeah, so that's like an interesting problem, right? But think about it like this. If this one is always rejecting, but it's actually still sending data, right? So there is a request of, are you alive? The server will never answer that request, but it will still send data, right? And we can see that it's sending data. So you can use that as a heuristic and say, this one's actually not dead. It just has some issue with the am I alive request. And you can do something about that.
This is a question about Datadog, your company.
Sure.
Like, what else do they do besides like managing servers and stuff like that?
So Datadog has like the idea here is like you can observe your your systems at the largest scale all the way to the service level scale. So I'm sure most of you are familiar with Java, so we can observe like the heap usage, all of the variables you're using, all the requests you're making, and then we can even observe to the more abstract levels of like what servers are running, what networks aren't running, and stuff like that. So it's all observability. That's our product.
What's your stack?
I don't have a stack. I'm like a DevOps person.
What do the engineers use?
Oh, all of our teams use different things. So I deal with Kubernetes, man. That's all I do every day. I use Golang.
Go away.
Yes.
Use Go. Shit's kind of fast.
Okay. I think this is done. If you have questions, I'll be here. Thanks for coming.